Hello, Math 1224. This is Dr. P with Lesson Launch 11.1, Manifest Density. So take a look at the solid object I've drawn here. This is it's a rectangular box. Doesn't have to be a rectangular box for the conversation we're having right now, but you may remember the idea of the density of a solid object. So imagine this solid object has some mass and therefore has some density. You know that density can be calculated as the mass of the object divided by the volume. And so the units of density will be equal to the units of mass over the units of volume, which are equal to kilograms per meter cubed or something like that. You could also talk about grams per centimeter cubed or kilograms per cubic foot, although they'd be mixing metric and imperial, which is kind of silly. But anyway, that's the basic idea of density, is that it's mass divided by volume. We can reinterpret that statement in the following way. We could say, so this is saying, suppose we know the mass and we know the volume, we can calculate the density. But what if we are given the density and the volume of an object, and we want to compute the mass? How do we do that? Well, if we're given the density and the volume and we want to compute the mass, then we go back to this relationship here, that density is equal to mass divided by volume, and just multiply both sides by the volume. That gives us mass equals density times volume. And that would give us a valid way of finding the mass of an object. Now this assumes that, change colors here, this assumes that the density of an object is constant across the entire object. And what we're going to talk about in this video is how we might operate if we could not make that assumption, if we have an object whose density is non-constant or non-uniform. But we're going to start with a simpler example here. So this was an example of a three-dimensional object, and we were talking about the relationship between density, mass, and volume for a three-dimensional object. I'd actually like to start by talking about a one-dimensional object. So let's suppose that I have a little steel rod here, poorly drawn. Okay, so a very Simpsons-ish steel rod here. Now this actually is a solid object, but we're going to treat it as though it's a linear object. And we're going to assign this some density. Now I actually don't know off the top of my head the density of steel, so y'all can have fun telling me I was way off with what the density of steel was. Well, of course I can make the rod whatever thickness I want and justify it that way. I'm going to say that this steel rod has a density of, let's say, 4 kilograms per meter. And let's say that this steel rod is 2.5 meters long. All right, so for now we're going to assume that this has a constant density, but you'll notice something funny about the units here. You'll notice that when I wrote down the density, I did not write density in units of mass per unit volume. Instead, it's units mass per unit length. And that's the point that I wanted to make here, is that density can be talked about. This can be mass per unit. It could be per unit length. It could be per unit area if you have like a sheet of something, or it could be per unit volume. Now in the real world, density actually it's determined by whatever material you're using, and that material will usually have a constant density per unit volume. So even the steel rod could be thought of as having a constant density per unit volume. But for all practical intents, if this is a rod and the rod's uniform, we can think of it as having a certain density per meter of length, and that density would be determined by the thickness of the rod. Anyway, so my question is, what is the mass of this rod? What is the mass of the rod? And what we do is we actually use a formula similar to the one that we had before. This density is density, or it's mass per unit length, and we're given the length here. So if we have mass per unit length, and we know how long the object is, then that total mass is going to equal I'm going to call it the length density, just to distinguish it from regular density, mass per unit volume type density. This is the length density times the length of the rod. And that's going to be 4 kilograms per meter times 2.5 meters. Oh, that was gross. 2.5 meters. And that's a total of 10 kilograms. That's 10, not 16. I need to work on my handwriting on this thing. 10 kilograms. There we go. Okay, I don't know whether that's a reasonable mass of a steel rod or not. You'll just have to take my word for it. Okay, so now the one other thing I want to do in this video is talk about what we might do if I had a steel rod and its length density were not uniform. So let's suppose I have some other steel rod, and I don't mean to make this look any bigger than the other one, but this is just so I can draw a little diagram in here. So let's suppose that this is a steel rod that for some reason the manufacturing got screwed up or something, so its density is not uniform throughout the entire object. Let's say it's lighter over here and then gets heavier, and it's at its heaviest on this end. Okay, so I'm going to just sort of fill some things in here. Okay, so the red dots are meant to convey the idea that as you go this way, the density increases. All right, and furthermore, I'm going to say that this rod, I'm going to say it is 6 meters long, and I'm going to say that the density varies linearly from end to end. And I'm going to specify that that density is, let's say it's 3 kilograms per meter on this end, right at this very end here. And then at this end, let's say the density is 7 kilograms per meter. So the density varies linearly from 3 kilograms per meter to 7 kilograms per meter. And by varies linearly, I mean that the density is going to change at a constant rate of change as I go in this direction. All right, so let's suppose I want to find out the total mass of the rod. What is the total mass of the rod? Okay, so I'm going to think about this question in the same way that, or a similar way to how we've been thinking about a lot of questions in this course. If I'm trying to calculate something that doesn't vary uniformly, or rather, well, I guess you could say a linear function varies uniformly, but something that involves a non-uniform calculation, then I'm going to chop this object up into tiny little bits. So I'm actually going to highlight this little piece of this rod here and assume that's tiny. Assume it's so tiny that I can treat the density there as though it is a constant. And I'm going to call that length there, I'm going to call it dx. I don't know if it's visible there, but I'm going to call that length dx. And I'm going to try and first find out, I'm going to first compute the mass of a tiny piece of the rod. And let's say it's x meters away from the light end. So we're going to say this is x. So the question is, what's the mass of that piece? So to figure that out, first thing I'm probably going to need to do is come up with some function that tells me how dense the rod is at a given spot. So the first thing we need to do is find a density function. Well, what do we know? We know it's linear because that was given in the problem statement. We know that that density function, oh, by the way, I'm going to call this something. I'm going to call this rho of x. So that's going to be the density in kilograms per meter, x units away from the light end. And so x is going to run from 0 to 6. I don't know if I've left myself enough room for all the info I got here, but that's what that density function is going to be. By the way, just for emphasis, this symbol here, it's not a P. It's called rho. It's a Greek letter, and it's commonly used for density, even for constant density objects. Anyway, this rho of x is going to be linear. We know that rho of 0 is going to be 3. And we know that rho of 6 is going to be 7, because 6 meters away from the left end. Those units should be meters. 6 meters away from the left end, the density is 7 kilograms per meter. All right, so how do I create a linear function such that rho of 0 is 3, rho of 6 is 7? Well, let's see. I know that every linear function can be written in the form mx plus b, where b is the value of rho of 0. Well, I know rho of 0 is 3, so I think that b is going to have to equal 3. And then m, that's the rate of change, the constant rate of change of this function. Well, I know that this function goes through the point 0, 3, that is x equals 0, rho equals 3, and 6, 7. So I can calculate the slope the usual way. The change in density over the change in length, that's going to be 4/6, that's 2/3. So I think my m is going to be 2/3. So I believe I can write down that rho of x is going to be 2/3 x plus 3. And anytime I write one of these, one thing I like to do is, check that the thing actually works. I really like people in a math class who are willing to taste their own cooking before they serve it to other people. So let's taste our own cooking here. So rho of 0, that's going to be, 2/3 times 0 plus 3. That does come out to 3, which is what we wanted. And rho of 6, that's 2/3 of 6 plus 3. That's 4 plus 3. That does come out to 7. So that does exactly what we want. So now I have my density function. And so now back to the question of what was the mass of that little piece of the rod. Well, that little piece of the rod there, I'm going to switch back to blue. There we go. That little piece of the rod, the mass of it is going to be the length density times the length of that little piece. Well, the length density is going to be rho of x, and the length is going to be dx. That rho of x, that's 2/3 x plus 3, and then the length of that piece is just dx. So that is the length, the mass of one of those little pieces. Now, if I want to know the mass of the entire rod, I need to integrate this from x equals 0 to x equals 6, and that's the last step of this problem, and mercifully, that's the easiest step. So now the total mass of the rod is going to be the integral from 0 to 6 of 2/3 x plus 3 dx. And I think that's going to come out to, let's see, that looks like 1/3 x squared plus 3x evaluated at 6 and 0. Thankfully, when I evaluated 0, that comes out to 0, so I don't need to worry about that anymore. I think that's going to give me 1/3 times 6 squared plus 3 times 6. And I think you should check my math on this, but that's going to be, I think that first term is 12. That's 1/3 of 36 is 12. And then 3 times 6 is 18. So I should come up with 30. Now, this is an actual problem with actual big boy units. Those units are kilograms per meter and meters. In the integral, what we're doing is we're multiplying some number of kilograms per meter by some tiny number of meters. So this answer, and in fact, this integrand here, both of these should have units of kilograms. So I believe that means the total mass of the rod is 30 kilograms. Now, here's a little secret. We could have known that without doing an integral. And that's because the density in this case varies linearly. Let's go back to this object up here, zoom in on it a bit. If I know that the density of this rod here varies linearly, then I know that in the middle of the rod, the density is going to be exactly halfway between 3 and 7. It's going to be 5 kilograms per meter. And it's exactly as much less dense over here as it is more dense over here. So I could have treated the entire rod as though it had a uniform density of 5 kilograms per meter. Well, 5 kilograms per meter times 6 meters, that's the same thing as what we got here, which was 30 kilograms. But anyway, I wanted you to see how to do this with an example where the algebra is not too hard, even though there's an easier way to do that example, because eventually we're going to do integrals where there's really just no way to do the problem other than to set up an integral. There's no uniform density treatment that you could do. Anyway, that's it for this video. In the next video, we'll talk about how to deal with area densities.